Hello and welcome to this lecture 4 on machine learning. Today we will build a probabilistic interpretation for machine learning concept of linear regression and also motivate regularization primarily by demonstrating how a linear regression model can tend to overfit. So regularization is affixed to the problem of overfitting. So recap that linear regression was found to be linear in the weights wi's, but it was not necessarily linear in the x. We introduced the basis functions phi. The basis functions phi could be quite arbitrary. We already pointed out that phi could be the radial basis function, or the Fourier basis, or you could also use wavelet basis or any domain specific basis. For example, with text documents, your phi's could be phrases. We also discussed the least square error minimization, and the minimum corresponds to E star. The corresponding estimate W star that gives you E star was also found with a geometric interpretation. So we found Y star in the column space of phi, and basically the W corresponded to the solution that gives you Y star that is as close as possible to Y, and this proximity requires that Y star is the projection of Y onto the column space of phi. We also found that phi transpose phi is invertible if and only if phi has full column rank. Now, is there a probabilistic interpretation to linear regression? So that will help us introduce a concept of a Gaussian error and also introduce maximum likelihood, which is an estimation process that will be useful for several other models that we will discuss in the course. The topics that will naturally be led to by our discussion today is that of overfitting. So we will introduce and motivate overfitting, but in the following lectures we'll talk of how overfitting could be addressed through a Bayesian approach to estimating parameters as against the maximum likelihood estimation. So we'll be building on the probabilistic interpretation and motivate the whole concept of maximum a posteriori estimates and more generally regularization, which is not always tied to probabilistic interpretation. And of course we'll see one more error function, and we'll bring up the more general question, the overarching question of how to minimize such complex error functions through level curves, surfaces, gradient vectors, convexity, necessary and sufficient conditions for optimality, and so on. We'll also discuss the gradient descent algorithm, which is extremely handy. So our model for probabilistically interpreting linear regression is that the error epsilon between the expected dependent output and the modeled output should be a random noise. Now, what does random noise mean? Well, first of all, noise means that it should be centered around 0. So the expected value of epsilon should be 0. And we also want that epsilon doesn't exceed some threshold as often as possible. So is there a distribution that gives us a nearly bounded epsilon? Yes, the normal distribution does. So you can show that the normal distribution n mu sigma square follows a very interesting rule called the 3 sigma rule, which is 68% of values drawn from this normal distribution are within one standard deviation from the mean mu. 95% lies within 2 sigma and about 99.97% are within 3 sigma. So 3 sigma basically covers everything. So you could say that epsilon is nearly bounded by 3 sigma square. This of course probabilistically. Is very high. What does this high mean? 99.97% or 0.997. Also, as an aside, given that we are unable to assert anything more about epsilon than that it must have some variance, specified variance sigma square, but other than that, you would like the distribution to be as free as possible, what will be the natural choice? Natural choice would be that which maximizes the entropy of the random variable epsilon, the entropy of the distribution specifying epsilon. And it turns out that such distribution is a normal distribution. Of course, we are interested in epsilon, that is real value. So the pictorial depiction of the 3 sigma rule is something we find useful throughout the course. So whenever you want a bounded value of the random variable, you might be interested in the normal distribution, especially if it's real valued. We also presented the entropy motivation. And as an aside, we note that the expected value of the normal distribution is basically W transpose phi x, which is the mean. So what this means is, on an average, even with this Gaussian noise modeling, the expected value of the output or the dependent variable will be W transpose phi x. This is basically a linear combination of the feature vectors. How do you find the W? So we were interested in a W that most likely is the one that generated the data, and that is the concept of maximum likelihood. So more specifically, we look at the probability of data given the weights. What does that mean? It's a conditional probability of the output variables y1, y2, yj, ym given the inputs x1 to xm. So this is the probability of having seen the data given the weights. And I just substituted the expression for the normal distribution of yj given xj. I've also made an important but a very commonplace assumption that the examples j equals 1 to m are IID. What is IID? They are independent. Each sample was generated independently and they are identically distributed. What does that mean? It means that the probability values come from the same template distribution called the Gaussian or normal distribution. So the template distribution is basically like the concept of a class in object-oriented programming. The specific value comes from that distribution, but that specific value could be very different for each instance, and therefore that is equivalent or analogous to the concept of an object in object-oriented programming. So an object is an instance of the class. It comes from that family. However, each object could have very different values of its attributes. That's precisely the case here. Now what is known here is the data and not W. However, what we want to do is find the W. So W is the variable or unknown. So maximum likelihood flips the view of this probability estimate, probability of data, and views it as likelihood of parameters. So from probability of data, here we move to likelihood of parameters, which we see here. So here we are finding the maximization or maximum over all possible weights of the probability of data given W. So this is also called the likelihood function, L of W given D. What will it turn out to be in this case? Well, a little bit of working around. The first step is to try and simplify a complex looking probability or likelihood of W given D. So recall that this is this complex product over J equals 1 to M of a normal distribution of Yj given phi of Xj W. And remember that this normal distribution has an exponentiated form multiplied by a normalization factor. Now a trick is to try and get this product of exponentiated forms into some kind of linear form. How do you do that? Well, we are interested in maximizing the likelihood. But what we note is that a monotonically increasing transformation, for example logarithmic transformation of L, will lead to the same optimal point, the point of maximum, as the original objective. So this is a trick. How this is the case will be a homework problem, a quiz problem that you need to solve. So this particular form called the log of likelihood is also denoted by LL, log likelihood. And taking logs, we find that the exponentiated forms, product of exponentiated forms becomes exponentiation of a summation, and with the log the exponentiation disappears. So this is basically the exponents. And the normalization factor appears in logarithmic form. Recall that the same normalization factor will apply for each Yj, Xj, because Yj, Xj are like objects coming from the same class, the Gaussian distribution, of which the Yj, Xj's are instances. So normalization factor remains the same, and therefore you have m times this normalization factor. Now recall that we want to maximize this log likelihood function, but this log likelihood function contains a sigma square, contains W, phi xj and yj. So phi xj, yj are known or fixed. W is unknown. What about sigma square? So we want to assume that sigma square is fixed, because that's something that is hinged on modeling of the error function. We'll realize soon that sigma square actually doesn't make a big difference as long as you know that the error is bounded. So for a fixed sigma square, W hat ML is actually just summation of these exponents and that is nothing but the least square solution. Thus, we got a probabilistic interpretation of least square solution, and the interpretation is that the error is normally distributed, examples are independent and analytically distributed. The next question we'll be interested in is how do we build on this probabilistic interpretation to do something more useful. So first question we'll address is addressing overfitting. And what is overfitting? I have provided a pointer to an applet. You could go to this applet and try plotting the linear regression function with different values of phi. So recall that phi could also be a polynomial basis. And what does this polynomial basis mean? It means that phi 1 equals alpha 1, phi 2 equals alpha 2 x, phi 3 could be alpha 3 x square, and so on. So you may take an arbitrary number of such phi's up to phi t, and we'll find at this applet that with increasing values of t, the norm of the w tends to increase. This is of course for the same or fixed set of points or data set. The other implication can be seen in this figure. So as you increase the degree of the polynomial, we not only find that the weights increase, but in fact the train error decreases. It's just because you have more degrees of freedom. You can always recover solutions with lower values of t from solutions for higher values of t. But the problem is, in the process of setting high values of t, you will try and fit every data point, and that's exactly what you see in this applet. What is the cost? The price you pay is that your test error also gets disturbed, and in fact the test error starts increasing even though the train error decreases. The test error actually decreases up to a point, but after a point you start overfitting. So these are two empirical observations. On one hand you have overfitting, and on the other hand you have the norm of w increasing with higher values of t. So the question we would like to address next is, can we address overfitting by restricting the norm of w, by making sure that norm of w shrinks? In fact, that is the concept of regularization. Regularization is about trying and suppressing norm of w. How can we achieve that? We'll do that through Bayesian linear regression. So Bayesian linear regression says that I have some background belief. What is the background belief? That the norm of w should have been less than some 1 upon lambda, 1 upon x. So Bayesian linear regression is about modeling a distribution on norm of w, or rather on w, and in the light of this prior belief, interpret the data and find parameters after having seen the data. In fact, there are multiple things you can do. You can either evolve probability of W given D, or you can look at the map estimate of W, which is that which maximizes this posterior. This probability of W given D is the posterior after having observed the data, and the prior is exactly what you assume about W, which is before having seen any data. An intuitive prior for the distribution on W before having seen a data turns out to be something we've already seen, which is we want probability of W such that norm of W is bounded. Now this should ring bells and motivate you to look at the Gaussian distribution once again. However, before we jump into Bayesian linear regression, we will motivate Bayesian estimation with a much simpler problem, and that of the simple coin tossing example, or rather the Bernoulli random variable.